Hello class, today we are going to start Algebra 2B Credit 1, which is exponential functions and equations. So in this lesson we're going to explore what are exponential functions, how can we graph them, and what do their equations look like. Going to the first few pages. This is our pacing guide. For this video, we're going to focus on lesson 13.1, exponential growth functions. And then following that, we're going to go into exponential decay functions. So before I begin, I just kind of want to talk about the difference between an exponential growth and an exponential decay, and what do their equations look like. So let's talk about a general formula for exponential functions, and that is y is equal to a times b to the x power, where b is called base. So this equation branches off into two pieces. The first piece is if b is greater than 1. And when b is greater than 1, that is called exponential growth. The second case is if b is between 0 and 1, so b is less than 1, and b is greater than 0. And what that means is a number that's between 0 and 1 is a fraction. So if b is a fraction, what we call that is exponential decay. So let's kind of look at some practice equations. So if I wanted to write an equation of exponential growth, I would just need to keep in mind that b has to be greater than 1. So one example would be y equals, let's pick any number for a, so let's say 2 times 5 to the x power. So 2 is actually the coefficient. 2 is a, so that doesn't really tell us if this is exponential growth or decay. What does tell us is this. So this number that has the power to the x, this is your base, and if your base is greater than 1, then this is going to be an exponential growth. So then for exponential decay, let's do another example. But in this example, we want to have b become a fraction. So again, let's use 2 for a, and let's use a fraction for b. I would just write 1 over 3 to the x power. So another example of growth is y equals, let's say a is 1, and if a is 1, we don't really need that coefficient, so let's say y equals 2 to the x power. So a is imaginary, you don't see that, but b is greater than 1. And for this example, for exponential decay, let's say we have y equals 1/2 to the x power. So again, a is 1, b is 1/2, and 1/2 is between 0 and 1. So lesson 13.1 is going to cover this part, exponential growth. Lesson 13.2 will cover this part. And the goal for lesson 13.1 is how can we graph exponential growth functions, and what are the transformations, and what do those look like? So going back to the packet, if we look at page 9, this is just a key summary of what we're going to be talking about. So let me kind of walk you guys through this. We talked about an exponential function. So it's f of x equals a times b to the x. Then there's a transformation for exponential function equation, which is this. So we have g of x is equal to a, b to the x minus h plus k. Now you guys might have already seen these before with different kinds of functions, with quadratic functions, linear functions. We have a, h, and k. So they kind of tell us what a does. These are the rules for a. If a is negative, that's a vertical reflection. If a is greater than 1, that's a stretch. If a is a fraction, that's a compression. Then for h, if h is positive, then the graph is going to shift to the right. If h is negative, the graph will shift to the left. And then k determines if the graph moves up or down. So if k is positive, that's a shift up. If k is negative, that's a shift down. We're going to explore these features. So this part right here is lesson 13.1. That's if b is greater than 1. This is for exponential growth. This is for exponential decay. And then there's more below that we'll talk about in the upcoming lessons. But we're going to focus on this on the next couple pages. So I'm on page 10. And again, remember that if you do not have a packet, just try your best to take notes. Make sure you label your notes, title your notes, and do as much as you can. I'm not collecting any notes. I am collecting homework, though. Okay, so exponential growth functions, again, are in the form of this equation. F of x is equal to b of x, where b is greater than 1. Now, previously, you guys seen parent functions, like of quadratic functions. A parent function would be f of x equals x squared, even parent functions of cubic functions. But in this section, depending on what the base is, we could have multiple parent functions. And what I mean by that is, let's say b is 2. This is considered a parent function. And let's say b is 10. This is also considered a parent function. Now, both of these graphs will look different based off what b is. And they actually kind of created a table, an x and y table, and they actually showed you the types of graph that these look like. So let me see if I can zoom in. So similar how you make a table, you plug in values for x, -3, -2, and then you will plug it in for the x up here. And you get some numbers here. And the same thing for the other equation, we get numbers. And then plotting those numbers. So here are all the points that were plotted. Look at the graph of f of x equals 2 to the x power, and then look at the one of 10 to the x power. So we notice some differences and some similarities. One similarity that we notice is when x is 0, y is always 1. So right here, when x is 0, y is always 1. And the reason that is, I'll kind of do this on the side. Let's say I plug in 0 into the first equation. So f of 0 is equal to 2 to the 0 power. But remember that anything to the 0 power is 1. So that's how they get the point 0, 1. Now this is going to be what we're going to be doing is we're going to create our equation, and then we're going to graph on Desmos to view our answer. So, John researches a baseball card and finds that it is currently worth $3.25. However, it is supposed to increase in value 11% per year. In how many years will the card be worth $26? Graph the function on a graphing calculator or at Desmos.com and use a graph to make the prediction. So we're going to start with our general formula, which is A of t is equal to p times 1 plus r to the t power. So p is the initial value and r is our percentage. So when we read this problem, it's currently worth $3.25. This is what p is, and this 11% is r. So on the side I'm going to write p is equal to 3.25, r is equal to 0.11. So plugging that in, I get 3.25 times 1 plus 0.11 to the t power, and that becomes 3.25 times 1.11 to the t power. So that's what a sub t is equal to. So this is the first equation that we're going to graph, and the second equation is when a sub t is equal to 26. So now let's go to Desmos and type those two equations. So the first one, a t is equal to 3.25 times 1.11, and then we're going to use this function here to the t power. Then my second equation is a sub t is equal to 26. Okay, so then let's zoom out and see where those two intersect. So it looks like it intersects around here. Okay, so at this point, 19.926 comma 26. What this tells us is it takes roughly 19.9 years so that the value becomes 26. So 19.9 is our solution. So we would write, to answer this question, it will take 19.9 years. All right, and that completes the first lesson. In the next page that follows, we have our homework. And let me just kind of walk you through the homework. For those that have the packet with them, you guys could do the homework on this on these papers, and then just upload the pictures through the Google Classroom. But for those that do not have this packet and cannot print the packet at home, what I would like you guys to do is, if you guys could copy the question and then write your answer on a blank sheet of paper. Make sure you label your questions. You circle your answers. And show all your work. I will be giving you guys a lot of points for showing work, even if the answer is incorrect. And do your best in trying to write your homework on a separate sheet of paper. And then you have the checkpoint. All right, and I'll see you guys next time.